As everything is getting quiet, let me welcome you all wholeheartedly tonight here at the premises of the Namibia Scientific Society. My name is Michael Backes. I'm currently the chair of the society, and well, as I said, in the name of board and staff, a very warm welcome. You might notice there might, as usual, be some people that will be coming late, but we will make them sneak in so that I hope none of you will miss too much. Let me, as I see a couple of unfamiliar faces, to me at least, introduce the Scientific Society to you very briefly. We just last week concluded our annual general meeting for the 99th business year, meaning next year we will celebrate our centenary, and there will be quite a couple of special events happening in that regard, so please stay tuned for those. The Scientific Society, welcome. The Namibia Scientific Society has a slogan and as motto, science for society. So while in the very early times we were essentially the only scientific institution in the country, way before UNAM or NAST were founded, we these days have a shifted role, and we try to bring science to the public, to you, both here in our room as well as those participating online. We do that with evening lectures like the one we have tonight. We do that with a yearly journal. We do that with books that we publish through our Cohesive Publishing House, and we do that through excursions that we run throughout the year. You will notice, welcome. The Society has a handful of working groups, and astronomy is one of them, actually being founded already in the 1930s. And tonight we will have one special talk on an astronomy topic of everyone's interest. It will be on the very elusive black holes. And our presenter tonight, I'm very happy to have her, is Professor Dr. Sera Markoff from the University of Amsterdam. She studied first at MIT, then at the University of Arizona in Tucson in the US, and then meanwhile moved to the University of Amsterdam and is a full professor there. She's highly decorated scientifically, and you can read most of that up in the announcement that you all have seen that made you come here in so large numbers. But let me highlight 2 points of her career. She has been, or still is, involved in very large astronomical international projects, one being the Cherenkov Telescope Array, where she was part of the scientific steering committee, so to say, and also in the Event Horizon Telescope collaboration. And well, you might have seen those pictures there at the back. When these pictures were revealed for the very first time, there was an international press conference. It was actually simultaneously internationally done, I think at 6 different locations. And the US literally flew her in to be part of the main announcement in Washington, DC. And so that gives you sort of a background of how decorated she is. With that, without any further ado, I want to hand over to Professor Markoff for tonight. Okay, great. And we're very much looking forward to your presentation.
All right. So maybe we can dim the lights now. Sorry, we're having lots of little technical snafus tonight. I hope it works out. Thanks a lot to, the Namibian Scientific Society. Sorry it's so binary with the lighting, but hopefully you'll stay awake for this. So this is my second time in Namibia. And as Michel sort of explained, I'm coming here in the context of a new telescope project, which we're developing in partnership with the University of Namibia, called the Africa Millimetre Telescope, or AMT. I'm afraid there will be plenty of acronyms in this talk, so I'll try to, it's just things become very long mouthfuls. Scientists, and especially astronomers, have a tendency to have lengthy names for things, so then we tend to make them into little acronyms. So just remember, AMT is the African Millimetre Telescope, and I'll be saying more about that. So I'm going to be giving sort of a little bit of a primer about black holes. I know there's been a couple other speakers here, and hopefully I'll give you a different flavor to that. And maybe as a just kind of audience participation, a couple questions. I wanted to know, how many of you in this room have seen one or both of these images before? So maybe this is somewhat self-selected. It seems like most of you have seen them. That's good. And now a second question is, how many of you actually have some idea of what these images are actually showing? Wow, I'm impressed. So it wasn't a huge degradation. So in this talk, what I'm going to do is give a little bit, hopefully something for everyone. So some history, a little bit about the thinking behind this. But the punchline of my talk is going to be these first groundbreaking images of two supermassive black holes. That's what you're looking at here. So let me introduce you to them. And so by the end of my talk, I'm going to get to really what we did and how we got these images and where the project is going. And what you're looking at is the light being emitted just outside the event horizon of these two supermassive black holes, and that's what we're capturing. And I'll give you lots of explanations so that by the end of this talk, you'll have a pretty good idea of what it is you're actually looking at. Now, this black hole on the left is called M87 star. That's what we call the asterisk, we say star, to tell you that we're talking about the black hole rather than the M87 galaxy, which it lives in. So we now know that almost every galaxy has a supermassive black hole in the center. This is a huge black hole. It's about 7 billion times the mass of our sun. Now, the size of a black hole scales directly with its mass. So when you say it's a bigger black hole, you mean it's both heavier, it's got more mass, and it's going to be bigger physically. This black hole, if you translate this into some size that it's basically our entire solar system, well beyond even Pluto, would rattle around inside the event horizon of this black hole. It's a monster. Now, the other black hole here is our own black hole, as you want to say, in the Milky Way. Now, for some dumb reason, we don't call it Milky Way star. That would make more sense. But because on the sky, it looks like it's in the Sagittarius constellation, it's named Sagittarius A star, or Sag star for short. And if you ever get confused between them, it's the clumpy one. And then M87 has this nice ring shape with a sort of bright spot. This is a pretty moderate-sized black hole, medium size. It's about 1,500 times lighter than M87, means 1,500 times smaller, but it's closer. And so in the end, these things look very similar on the sky in terms of their size. And we'll come back to that. So, we've learned a lot from these black holes. I'm going to be telling you a little bit about it, but I want to start with one of the first things that we learned that I think was pretty surprising to a lot of us, which is that they make really good memes on social media. As Mikhail mentioned, I was part of the team that presented these results to the world for the first black hole, M87, in 2019. And we're scientists. We're a little bit nerdy. We don't really expect people to think what we do is that interesting. And we were sort of taken aback by almost immediately the response of this kind of imaging. And I started thinking, why? What was it about this? Is it the fact that it's a black hole? Is it the fact that it's the way it looks? And excuse me, I think it's a little bit of both. So part of it is that humanity has had access to the sky for all of its history. And I think we tend to be fascinated by the sky because we sense there are mysteries out there, and mysteries tend to be a bit scary. And when things are scary, and especially black holes, I think sound pretty scary, there's a human tendency to try to familiarize, control it, have a story, have a narrative, but also maybe do silly things with cats. And I think that that's one reason that this black hole became something people found very familiar and they could lock onto. But there's another reason that I think particularly this image might have had some resonance. And so imagine that you were living somewhere 10,000 years ago, and you only knew what was out there in the sky, and you made your stories about this. What would be the scariest thing that you could see out in the sky? Anyone want to venture a guess? Some kind of celestial object or event that would directly impact you. Audience participation time. Well, that's certainly true, but let's say that that's a pretty rare event. What's a more common event that could happen during your lifetime, which would be pretty terrifying. If I'm hearing a lot of things. Asteroids, what about if the sun goes out? Yeah, I heard that. The eclipse. So this is an image of the solar eclipse from last year, totality in Mexico City. We were actually in Mexico for the EHT, or the Event Horizon Telescope project. Now, just to make it clear, the Event Horizon Telescope, or EHT, is the bigger project that took these images, that I'm part of that team. But the AMT, as I'll explain later, is going to be an additional expansion of this project, and I'll say more what that means. But so we were there for our team meeting, and this happened a few months before. And, you know, imagine you saw the sun go out. Has any of you actually been in a total eclipse? Can I see some hands? A few? Yeah, so, you know, we know, right, what this is. It's a pretty mundane event. It's just geometry. You basically have the moon moving into position, and it's blocking the light of the sun. It doesn't sound that scary when you put it that way, but if you didn't know, and you don't know, and even if you do know and you've lived through it, and I just want to advertise, you have 6 years to get ready, because one is coming through Namibia in 2030, and it is an amazing event to go through, but it's still pretty scary at the time. And the thing is, there's actually some commonalities here with the image that we're looking at, and I think this inherent kind of sense of maybe like a fear or wonder that people feel during the eclipse gets transferred to this image. One thing that's interesting to note is it didn't have to be this way. It's actually quite a coincidence that the moon is exactly the right size and distance to block out our sun like this. I mean, it could have been any random combination. But the black hole image is somewhat similar for different reasons, right? We're not having a solid object blocking the light. But what's happening is you have this thing called the event horizon. There's no solid surface, but the light is being just sucked up and eaten by the black hole, leaving the backlighting of what's around it. So you can kind of understand where the eclipse plays a role in this, just to understand a bit about what we're seeing, but I'll show you really what we're seeing in a little bit later. And the eclipse played, interestingly, an important role in the history of getting to the point where we could study black holes. So also relating to Mexico City, I just wanted to mention, it was like, I was always kind of interested in indigenous cultures and what people think about astronomy. And the Mesoamerican peoples had a very rich astronomical kind of mythology, but they also were very impressed by eclipses. These are historical records at the time of the Spanish conquest, documenting different eclipses that the Aztecs wrote down, where they drew pictures showing, you know, basically bites out of this thing called the sun. They associated it with wars and with disasters. And they had a pretty scary mythology that the sun was being eaten, you know, by animals or some kind of demons that had to fight their way up through the night. So it was a very apocalyptic view. During the eclipse, this really activated them to think about these kinds of monsters eating the sun. But they're not totally wrong. And by now, actually, we know, now this is not a real image, this is what we call an artist's impression, that there are black holes, in fact, millions of them in our own galaxy, that eat suns all the time. So that's the ultimate eclipse as far as I'm concerned. And this is a movie showing you a kind of image of what this looks like. So actually, most stars are born in pairs. Our sun is a little bit of an exception to that. And when a very massive star explodes at the end of its life, becomes a supernova, it will leave behind a black hole, and it can stay in a pair, and it will start to consume its companion star. And so I wanted to say a couple things about this. First of all, because the first black hole that we discovered actually wasn't the ones in the centers of our galaxies. Those are the first that we made images of. But actually, the first black hole we really discovered as a candidate real black hole was one of these stellar mass, tiny, you know, the size of a star, way too small to do a direct imaging. So we found it in more indirect ways. The other thing to note is that people ask me all the time, wait a second, if a black hole is absorbing all the light, how can you see it? And this lets you see that when a black hole is stealing material and able to capture it, it spirals into this thing that we call a disk. And then sometimes material will get ejected from, not from inside the event horizon, but from just outside, and will be spouted out in these things that we call jets, which can move at the speed of light. They're basically full of magnetic fields, and I'll show you some actual picture of what that looks like. But this gives you an idea that the light is actually created by these structures. These are things we as astrophysicists are very interested in understanding, and then this is the light that backlights the black hole, and that's why we see the shadow imposed on top of it. So for the rest of the talk, I'm going to basically go back a little bit to just talking about the history, where we started thinking about these black holes, where did this come from, and gravity. And then I want to say a little bit about the astrophysical role of black holes, because I'm an astrophysicist, so I'm interested in this ecosystem that black holes live in and what are they doing there. And I think that this is actually, if you're used to thinking of black holes as these kind of cosmic, vacuum cleaners, they're actually a lot more interesting than that. And then I will come to, with that context in mind, I think it'll make more sense, what it is that we're doing with the Event Horizon Telescope and where the AMT comes in. Okay, so let's talk about the beginning. Now, when you think about gravity, the daily experience of gravity is something like, we call this a force, right? It's something that we feel, a massive object is enacting a force and sort of pulling things towards you. We stick to the Earth because the Earth has gravity. We also have gravity, but it's almost negligible. And the Earth pulls us to it with this force. And that's the way that Newton, who you've probably heard of, the guy who saw the apple fall, that was his idea of how gravity worked. And another force that you're probably familiar with is the electromagnetic force, what makes magnets work. And forces can balance each other. So if you take a heavy metal ball and you pick it up with a magnet, you're fighting gravity. So you're actually winning out with the magnetic force over gravity. If you turn the magnet off and the ball drops, gravity wins, right? And this is a way that Newton would think of gravity, and in fact was the way we thought of gravity as a force like any other for hundreds of years after Newton. And then Einstein came along just over 100 years ago, and he basically just said, nope, this is not correct. What he said, in fact, was very weird. He said, you know what, we think we live in 3 dimensions, but actually we're sort of living in 4 dimensions, that we're living in this sort of fabric. Now the problem is we use these words that are like words that we're used to, like fabric and bending and so on. It's very hard to get your mind around 4-dimensional space if we're a 3-dimensional beings. And so we come up with these analogs that are simple and not entirely accurate, but they'll help you understand a little bit about how this all works. So what Einstein was saying is there's this 4-dimensional space and time are knitted together called space-time. It's something like a deformable fabric. And if you have a massive object, it can warp this stuff around it. And then that forces things to move in a particular path that looks like it's being affected by gravity. Now, if that sounds crazy, people thought it was crazy at the time, so now we've accepted this, but at the time he said this, people were like, no, this is crazy. There's a little movie, we often do this when we try to explain black holes to kids, but we take like a heavy ball and we put it in a rubber sheet, and then you could say, okay, let's just throw a marble past this, what's gonna happen? So if there was no rubber sheet and no massive object, the marble would go in a straight line, right? But because you have this warping, the marble, if you give it enough energy, can actually pass, but its path will be bent. And if you don't give it enough energy to escape, it gets bound into something like an orbit. Now, what's happening is, of course, it's being forced into a path by this bending of this, in this case, rubber sheet. But what you can think of is that space-time is doing something quite similar. And so what happens is we think that things are bound, like planets are bound around the sun by the sun exerting gravity, but what's really happening is the sun is bending space-time around it, and the planets are being forced into a sort of path like this. And the interesting thing is that light lives in space-time as well, so even light has to move and get bent. And of course, if you run, this is not a black hole, it's a black ball, but if you ran into a black hole, you would get sucked in this case. So one of the things that this also illustrates, let me just show this one more time, is the fact that you can, if you just have the right trajectory, you can orbit a black hole for a long time, just like planets orbit the sun without falling in. And so that helps explain why you can have structures right outside the black hole that are quite stable for a very long time. It's the same gravity that keeps us from falling into the sun, and we've been doing that for billions of years, right? Okay, so people often, use these kinds of illustrations to think about the deformation of space. Everything that has mass deforms space. You're deforming space, I'm deforming space, but it's just a tiny amount. But the key is not just the mass, but it's how much mass is put into how much volumes. We call that often density or compactness, and the more compact, the more space-time will be deformed. And so you can think that the sun will deform space-time a bit. Like a small sun like ours, a star like ours, our sun, when it hits the end of its life, will form what's called a white dwarf, which is a compact object, but If you have a bigger star, it will have a supernova, and it will form what's called a neutron star, which is even more compact. And finally, that kind of black hole system I showed you will form, which is called a black hole eating a star, or it can even be on its own. And basically, you also get these in the centers of galaxies. You will have something where the space-time is so deformed that you form something like an event horizon, this point of no return. And it's not a correct exact physically to say this, but what you might want to think is that space-time itself is kind of almost fluid. It's not static. So one way that I find easier to understand is that you can imagine that the black hole is sort of dragging space-time towards it. All these objects are dragging space-time towards it, and things get stuck in it. But at some point, you hit a point where space-time is actually moving at the speed of light. And so even light is like a salmon, swimming upstream, and it can't really escape. That's just a way, it's not exactly mathematically correct, but a kind of way to build an intuition about this. So when Einstein had these ideas, I should say Einstein in this room, yes. But when he had these ideas, people thought it was crazy. They thought he was off his rocker. But there was an easy way to test it, which is that the sun, by bending space-time, the prediction would be that if the sun's in front of the stars that are sort of way far away in the background, that if you look at the sun during something like an eclipse, so we're coming back to the eclipse again, then you can see the position of the stars and measure that deformation compared to when the sun's not in front of them. And so I find it kind of interesting that, in 1919, the world had just gone through its first World War, but gentlemen of leisure, like Lord Eddington here, means and leisure, just decided to test this idea, and Africa played an important role. Actually, they went to a full solar eclipse that was off Western Africa on the island, I think it's pronounced, I don't know if it's pronounced Principe or Principe, but they tested it there, and there was also an expedition to Brazil, and this is picture of the actual photoplate. What they show, it doesn't have the labeling on the photoplate. That's something we put. But you can see there was actually a bright solar flare at the time. But these stars were the stars that were used to actually measure it. And sure enough, they saw a deformation. So Einstein became famous basically right then. And general relativity, this theory of gravity being a byproduct of space-time bending, was generally accepted at that point. So how do you go from this to black holes? That would be another lecture entirely, but you can kind of imagine that people started to understand the mathematics and the physics of this weird space-time, and they predicted that you might have an object that could exist inside its own event horizon, such that it may even be a bright object, but the light would never get out and you wouldn't see it. And this was mathematically possible, but people didn't believe it. Einstein didn't believe it for many, many years, and it wasn't until the 30s when, have you seen the movie Oppenheimer? It's that Oppenheimer, but he also did quite a lot with astrophysics as well. And he and Snyder wrote a paper basically showing that a star at its end of its life can sort of expand and then collapse and smoothly progress through its own event horizon. And that kicked off the idea that something like this could actually exist. Now, they didn't have a good name for it yet. They called them gravitationally completely collapsed stars, which was a mouthful. And if you want to know the story of how they got to the name black holes, which came in the 60s, it's a Shaggy Dog story, and you can ask me that during the questions. It's kind of interesting. But okay, so then how did they actually go from 1939, thinking these things could exist, to actually discovering them? And that took space. So what happened was you can't really see black holes very easily with your eye or with the optical band. And so you have to start looking at other types of light. So I'm going to just flash something probably many of you already know about the electromagnetic spectrum, but light comes in many colors and flavors. We see with our eyes only a very small part. Long wavelengths go down to the radio, and the shortest wavelengths go up to what's called the gamma rays. And this drawing here shows you kind of what the atmosphere absorbs away. So if this color bit gets down to here, it means that you can see these from the ground. So radio microwave, you can see from the ground. Visible, this is why we can see the stars at night, gets to the ground. But everything like very high energy stuff like ultraviolet and X-ray would kill us, actually. So it's actually good that the atmosphere absorbs all of this away. But it meant we had to go to space to be able to see that. It turns out that black holes are very bright in the X-ray. Gamma rays, technically you can't see them from Earth directly, but as you may know, there's the Hess telescope in Namibia here, about an hour's drive away, and that sees gamma rays from the ground, but it's not seeing the gamma rays themselves, it's seeing their byproducts. It's sort of a trick to see how it gets to the atmosphere. Now, millimeter band is a shortest band in the radio, and technically you couldn't really see it from Earth, but if you go to a high mountain and you go to high and dry, that's why Namibia is quite good for this. So you need to go to high and dry places to be able to see in the millimeter, and I'll say a little bit later why, but this is the wavelength that we use to study the black holes and make these images. But what happened was, basically, Sputnik in the 1950s, many of you might have heard of this, there was the first probes of space that the Russians did, freaked the Americans out, so they created, in panic, the Space Act and created NASA. There's Laika, was the dog that went up with the Russians. The Americans started to send sounding rockets into space, and they were looking to find X-rays that they predicted would come from the sun and maybe bouncing off of the moon. But instead, they found really bright sources that they didn't know what they were. They were clearly astronomical, and it turned out that they were these remnants of things that exploded, stars that exploded and became neutron stars eating a companion star, and black holes eating a companion star. And the first black hole that was found was one like this movie I showed called Cygnus X1. It's about 20 times the mass of our sun. That's a pretty big one, actually. They usually range from a few to about tens of solar masses. And this was already discovered in the 60s, and then that was with the X-rays. And then slowly people started to also use the radio, and around the same time they found the first supermassive black hole candidates. Now, I won't go into the details of how you weigh these and find these, but just you can ask me about that later. But these are different than direct images. You sort of infer the mass or of the black hole by looking at the gravity of stuff that happens around it. So that hopefully gives you a bit of the history there, and the lead up into the fact that by the 60s, we really had a sense that black holes really existed, but it took decades from first coming up with this idea of gravity, understanding that black holes could exist, and then finding them and finding the first candidates. And now we want to talk a bit about what black holes do, and then I'm going to go into the telescope project a little bit more. So people are often quite stressed out about black holes, as I mentioned. There's a sense that, wow, we have a black hole in the center of our galaxy. Isn't that a bit dangerous? And I wanted to reassure you by just saying that black holes are actually quite harmless. They're mostly in their dormant state. And as long as you don't fly yourself into their event horizon, which is, you'd have to purposely do this, you are pretty safe from them, at least the one in our galaxy. And so this is not our galaxy, but if you could fly out of our galaxy, it looks something like this. This is the M81 galaxy. It's a nearby one. It's kind of a twin. Now, if you think about what is the reach of a black hole, like as in, if you were near a black hole, how near is too near that you would get sucked in? That would be the place where the gravitational pull of the black hole or the deformation of space-time is strong enough to weigh out over the things that keep you where you are and pull you in. And that reach of the black hole is typically on the order of about 100,000 times the size of the black hole. Now, that sounds big, but on this picture, if you take our black hole, imagine this is the Milky Way, you couldn't even see it in this dot. It's tiny. And our galaxy is about another 500,000 times bigger than the reach of the black hole. So we're out here somewhere in the suburbs of our galaxy, and we are completely safe from the black hole. In fact, you could replace Sagittarius A star with a rock, and it would do all the same things, more or less, at the moment. Well, not everything, but at least from the distance, the gravity part would be the same. Thing is, they're not always dormant, and when they get enough material, when they capture something like a black hole in the center of a galaxy can capture a star, or it can capture some gas from nearby, then it gets what we call activated, and something very different happens. And so what I'm going to show you is, this is a picture made with optical light using the Hubble telescope, which probably some of you have heard of. And this is not stars. Each one of these is a galaxy. This is what's called a cluster of galaxies. They're basically bound together by their own gravity. This is kind of the birthing place of galaxies. You can think of this as a nursing ground in a way, and how galaxies form and grow in these clusters like this. So if you look at this, you can't really see where the black holes are. You're looking at all the optical light from all the stars in the galaxy. This is, again, to emphasize why we need to use other wavelengths to study black holes. So now I'm going to change to show you two other wavelengths. The ones I was talking about, radio, which is these long wavelength things that we can do from the ground, and X-rays from space. We use false colors because you can't see them with your eyes. So blue is radio, pink is X-ray. This is one galaxy that has one supermassive black hole in the center. And these are those jets that I was telling you about that can be ejected from the black hole. These are about 1 billion times bigger than the black hole. You know, the galaxy is here. These things go way beyond the galaxy. They actually interact with everything around them. This pink stuff is X-rays, which means that the gas of space is, you know, as cold as it can be, like pure 0 degrees. And then basically, you're heating all this gas from the action of the black holes and the interactions of these galaxies up to millions of degrees, like the solar corona. There's a lot of energy there. And you can also use this gas to see that the jets punch through all this. They're so powerful, they are basically depositing the energy of about 100 billion supernova, one black hole. Okay? And each one of these has a black hole in it. This is an active one, and it's pushing the gas out of the way. We would really like to understand how this works. We think that this can actually change the evolution of the galaxies, both the hosts and the galaxies around this. We think the universe looks the way it looks today because of this kind of feedback effect and this interaction with black holes, among other things. And so this is something very important for us to understand. So black holes are not always dormant. They can be extremely active in this sense. But you'll notice that these are sort of a panorama of many other kinds of objects. These are the black holes, small ones. And sorry, this is a small one, this is a big one. But these are things like forming stars, planetary nebula, supernova remnants. This is a pulsar wind nebula. There's many astrophysical objects out there that are not black holes, but you see a lot of similarities with disks and jets. And so there's a sort of generic physics of gravity-powered things that happen in outer space that we would like to understand. So black holes, in a weird way, are almost simpler than some of these because they don't have a surface, and we're trying to understand this. So that's just a bit of the background, and now I think you have a kind of a bit of a sense of the history and what black holes are about. Let's start talking about the project and what we were doing. Okay, so if you're gonna try to see a black hole, I guess the first thing you need to know is, what are you looking for? So we know that a black hole is going to deform light. We need to start making models of this. And the physics of how light is deformed around a black hole is something that was mathematically worked out already almost 100 years ago. But now we can make cool computer animations to try to show you a little bit of what's going on. So what I'm going to show you is a movie. You can imagine that this is the camera screen or the telescope at infinity. And you have a black hole here. And imagine it's surrounded by a disk and a jet that's giving off light. We're not going to show that. We're just going to show the trajectories of the photons, the rays of light. And it's something we call ray tracing, which is the same thing that happens if you play video games. There's ray tracing to make the light and the perspectives look good. And so we tend to divide this up into the direct light that comes to you versus the light that will get stuck in orbit around the black hole several times, like we were showing with the marble, before it will actually escape. And so light coming from sort of behind the black hole coming to us here will get bent, as you'll see the trajectories, but it's mostly remaining intact. And you see the black hole will absorb the light, and you get this dark spot there. And that is the majority of the image that we're looking at is what I call like the astrophysical fluff. It's coming from the astrophysics. But then there's all the photons that come in, make 1, 2, or even hundreds of U-turns and can still escape, and they get very focused by the gravity into this bright ring, which is often called, not so originally, the photon ring. And this is a direct prediction of general relativity. The size and the shape and the distortion is something that we can predict. Roughly speaking, it tends to be around 5 times bigger than the event horizon. I'm going to show this again because what you're going to see is, oops, sorry. What you're going to see is that the light that's bent means that it comes out at a larger radius than the black hole. So that's what we call gravitational lensing. Gravity acts a bit like a lens, like a magnifier. So that's why the ring ends up being 5 times bigger. And one of the problems that we have is that if you're interested in testing Einstein's general relativity or seeing if it's wrong and finding out another theory, you really need to understand this ring, which is about 10% of the light in the image. The rest of it is coming from this astrophysics. So you need to know both. You need to understand the physics of what's happening around the black hole and all this kind of stuff, the jets and the disk, but you also need to understand space-time. And our problem is picking these things apart because our images are just not good enough. But before we had images, we were trying to think, like, could we actually find this thing? And so if you know what size it needs to be, if you know your black hole mass from some other measurement, and you know its distance, you can predict exactly what size it should be on the sky if general relativity is correct, and then you can go figure out if your telescope is actually good enough to do this. So what we found out was that for the nearby black holes that we thought we could target, we basically needed a precision on the order of about 20 or so micro arc seconds. And that, to give you some idea, would be taking a telescope, like up to your eye or your binoculars, and reading a newspaper in Cairo or something from Windhoek. So on the order of 6,000 kilometers, you'd be able to read a newspaper. It's extremely precise. And to do that, you need a telescope that's basically the size of the Earth to be able to do that. Now, you could, of course, build a telescope the size of the Earth. This would be gravitationally unstable and not really nice for the people living underneath it. So we did a trick, which is called very long baseline interferometry. It's a technique where you take telescopes across the Earth and you string them together into an array. And it's an effective telescope the size of the Earth. And what's important is that the bigger your telescope is, the further you can see. We substitute these, what we call baselines. The distance between these different dishes gives you the tuning of the telescope. So the worst that you can see in some sense are these short baselines. This tells you what the largest structures you can see. And the longest baselines, the size of the Earth, give you the smallest thing that you can see, which is about the size of the black holes that you're looking for. And you need to find the right black holes. It's a bit of a Goldilocks problem that have exactly the sort of ring size and brightness to fit in this tuning. And then also, of course, this isn't an Earth-sized telescope. It's a trick, but you don't have a lot of collecting area. These are smaller dishes. So you actually, the more telescopes you have, the fainter an object you can see. And these are the limitations that we had. And so the concept of this was around for a long time, but to do this in the millimeter band, this higher frequency band, or shorter wavelength, I should say, we really needed new technology for that. Also, actually, I should say, just running this again, but keeping in mind that the data rates are enormous for this. So basically, on a given night of observing, we have petabytes of data. 1 terabyte drive, you could think it's about this big these days. A petabyte is 1,000 of those. And there's no way you can send this over the internet. So when we do this, you effectively have these stations, like in the South Pole, and you have to wait until you can get all the data on these hard drives packed into boxes and shipped by air to supercomputers, which then post factum put everything together and can make the signals. It's a very, very technologically challenging process, and that's why it couldn't happen until around this time. So anyway, who was crazy enough to do this? Well, it was a group of people, did a lot of testing. We came together as a collaboration formally only in 2016. And we did our first data, which is the images that you saw, in 2017. So that's extremely fast. And the reason was because we were borrowing these other telescopes. But we're an international collaboration of hundreds of members. I have to mention that I am representing the team when I'm showing these results. So this is really a group effort across many time zones. During the pandemic, we had to do a lot of our work online. And the last few years, like I mentioned, we were in Mexico City last, Taiwan, in Granada and Spain. We meet around the world, but we have midnight, 2 a.m. telecons. We have to spread the pain fairly among the collaboration to do the work. So I say living on borrowed time. So this is our array as it was. We don't own these telescopes at the moment. We're borrowing them from other people. And in astronomy, the telescopes are usually owned by consortia or institutes, and you have to apply for time. So we have to apply to get the time that we use this telescope in this mode. It's put into this mode where they can all talk to each other for about 2 weeks every year. And so we only get to look once a year. We're given usually about 6 nights, or it can be during the day, because radio doesn't care about the sun so much. You can also do day observing. We get 6 days. We have to try to trigger for the best conditions, the best weather, everything across the array. In 2017, we had 8 facilities. We didn't have the Greenland telescope. We added that in 2018. Most of what you've seen so far is from 2017, but we have been observing ever since. And the reason it took so long was because everything had to be done completely new. Nobody had ever done these things. Now we're kind of into production mode, and you can start to imagine we're going to have more and more results coming out faster, and I'll show you a hint of what's happening towards the end of my talk. We grew the array between 2021 and 23. We lost some years to things like global pandemics. We now have an array, a new array near France. We have one in Korea that we added in. We also tested a new frequency or a new wavelength, which is even shorter, which gives us even better resolution. So that's something else that's in development. And one of the things that I do is I'm also in charge of trying to coordinate, along with another team, all the different, we try to look at the same time we do this with the Earth-size array, we try to look with other wavelengths of light. So we try to coordinate on space and ground, and I'll explain what I mean by that, to try to get more information, because as I showed you, one wavelength doesn't give you all the information. That image I showed with the big jets, that was combining different wavelengths, so we need to combine information ultimately to understand these things. So what was kind of the punchline for at least testing general relativity is that we know the mass, we know the distance of these black holes, so we can predict the size in what we use these units of micro-arcseconds. Again, this is this tiny, tiny thing on the sky. And then we have these images, and lo and behold, they sort of line up with the prediction. Now, that's not the way we do it. We don't by eye kind of say, but it gives you the idea. And then the way that we actually test whether, for instance, how consistent this is with general relativity really is a very, very detailed, and this took years of work, and I'll just try to give you a sense of this, but what we do is we make computer simulations, and we basically take a black hole, and we put it in a computer. I mean, not really, but like we make a model of a black hole in this distorted space-time, and we wrap material around it, we put in magnetic fields, and we test different initial conditions, we let it run, and then we do this thing where we try to make the light and do the ray tracing where it goes through the gravity, and we make fake images from our models, and we try to decide, does this look like the data? And so this gives you an idea a little, I'm not going to say too much, but anything you see in orange are members of my group, students mostly, past and present. So these are simulations that were developed in my group. So what you're seeing is a top-down view of this disk around the black hole, and this is a side view, like a slice, where you see this kind of donut of material, that's the disk, wrapped around the black hole, seeded with magnetic fields, and then we let it run. And so you can see the magnetic fields sort of get all tangled up, and you start to launch, those jets come out, and here's like showing you the structures of the magnetic fields, and you basically, we run these things in real time. These are extremely computationally expensive. We're using millions of CPU hours or hundreds of thousands of GPU hours. And then we try to make an image of it. Now, what you might notice, though, of course, is that this doesn't look like the ring, right? Where's the ring come into this? And this is a nice visualization that tells you that what you see is dependent on the wavelength that you're looking at. And that sounds kind of weird, but if you think about this, like if I'm looking at a human being, I see their skin, right? I see a human surrounded by skin. But if I look with X-rays instead of optical light, I see right through you, right? That's what X-rays are, a different kind of light, and they pass through you, and you can see, don't see the skin anymore, but you see like the bones and other things that are inside. So when we go to different frequencies or different wavelengths, we're actually able to see different parts of the system. In the low, the long wavelengths, the radio, we see the jets and we see this large structure in the disk. But if we go to the millimeter, which is shorter and shorter, and also the X-rays, it's like we can pass through and we start to get down to what's happening near the black hole, and we can isolate this region, and that's what the Event Horizon Telescope does. We actually have access, as I showed you pictures, we know what those big jets look like. We're trying to understand what's happening down near the black hole, so we have to tune our telescope, tune our frequency, and then later we try to put it together with these other telescopes and reconstruct, every piece of the system, but we can't see it all at once. So it's a very complicated thing that involves many telescopes, actually. So then, for every model, we generate basically a movie. And so this is the model, and what you can see is there's the astrophysical fluff, and then there's this thing that doesn't move, and that's the space-time general relativistic part that is basically a prediction of Einstein's gravity, and the rest is stuff that's maybe changing because it's moving, it's orbiting, and there's like a lot of complicated dynamics happening. And then it gets blurred because we have this, well, I won't say terrible telescope, but it's the best we could do, but it's not great, in the sense that we only have a few telescopes instead of an Earth-sized array. So the only way we can improve on this is to go off the Earth to space to be able to have longer baselines, and we need more light to come in to get more sensitivity. So the problem, though, is you can imagine that if we had a movie, we could easily pick apart this ring from the stuff that's changing, because one part's not moving and one part is. The thing is, when we only get to look once a year, we're just getting a snapshot each time. So it's very, very difficult for us to decide which movie's correct because it's changing all the time. So what happens is we run many, many, many computer simulations. This is just a small sample. By now, we're actually up to hundreds. I'll give you an example of this. And then we basically try to rule it out in different ways. We're stuck sometimes with the first black hole, for instance. These are 3 completely different models where we sometimes change things about the black hole, sometimes change things about the stuff around it. And at the end of the day, when we blur it, so this would be like if you had a perfect telescope, and this is with our telescope, it looks identical. So we cannot tell the difference between certain types of models. And this is the limitation at the moment in testing general relativity and testing some of these ideas. We do a pretty good job, but we can't be 100% sure at the moment. So now what we're trying to do, and this is where I'm getting to the last part of my talk, is what can we go for, how can we go further, and what is the next steps in this project? Okay, so this is the state of the art now. These are the 2 images, and you see this kind of, as we would say in the Netherlands, Van Gogh, or Van Gogh, as you might say, style art, striations. But these show us what's called the polarization. We know now the polarization tells us about the geometry and the structure of the magnetic fields. So now we have information not just about the light, but also the magnetic field direction. And that helps us rule out quite a few of these different model space. We have all these different movies we're trying to understand. And it gives us a lot of other information. And one of the things that's been surprising is, remember I was saying there are 2 kinds of black holes, dormant ones and active ones. And then there's also supermassive and stellar, but these are both supermassive. Sagittarius A star in our galaxy is dormant. But M87 is active. So this is the M87 galaxy. It's a big elliptical galaxy. This is the image from the Hubble telescope of its jet. So it has clearly one of these massive jets that are millions of times bigger than the black hole, basically punching through the entire galaxy. And then, we have this image, and the similarities between these images both tell you that the image is dominated by gravity, but what's puzzling for us is that the magnetic field structures seem to be very similar between these 2 black holes. And that was not expected, because we thought that you would need sort of special magnetic fields to give you this jet. And then in Sagittarius A star, this is, imagine the galaxy. If you zoom in to the very center, we see this kind of spiral of stuff feeding the black hole. And we don't see any sign of a jet at all. And we have pretty good telescopes. It's a pretty nearby black hole by our standards. So there's something weird. Either there's something wrong with our models, or we're not finding the jet. Maybe it's pointed in a weird direction or hiding. So there's a lot of controversy at the moment about how this all works. And maybe some of the difference has to do with how much power the black hole is able to get at the moment. But that's one of the state-of-the-art questions at the moment, and we need to try to understand this better. So one of the new horizons is that we need to start accounting for all the light in all these different wavelengths. So this was, I sort of had a version of this from this is from 2017. From 2018, that was the poster for this talk. At the exact same time we took this image, we took all of this, of the entire system. So here's the Hubble image showing the galaxy with the jet. We have X-rays and on UV. We have X-rays here from the Chandra telescope. So these are all in space. We have all these ground-based radios showing you different views and details of the jet. We also have what are called, here is the gamma rays. So here's the HESS telescope here in Namibia, an hour away. And what we need to do is start to combine all this information so that we can start to understand the bigger picture of how this black hole manages to launch these jets and go into this active state. So that's something that we're doing at the moment. For Sagittarius A star, we're also trying to combine light from different frequencies. So here's the frequency or the wavelength that we use for Event Horizon Telescope and AMT with that spiral of gas. And it's flickering. The black hole's flickering in every wavelength that we look at. It's like solar flares. We're looking at something like solar flares right outside the black hole. And we think that if we can make a movie of this, if we can improve the telescope, we can actually resolve these flickering into, just like we see solar flares on the sun, like big arcs of stuff. We think that that's happening near the black hole. We'd really like to understand that because that tells us things about particle physics, and I won't get into the details of that, but that's a very important question for us. But if we use those constraints, now, by the time we did Sagittarius A star, it was later, we had hundreds of these models. The size ruled out just a few because we kind of knew what we were expecting, but the shape ruled out a lot of our models. As we started to put in information from all the different kinds of light, the spectrum, we got it down to 4 out of 200 models. And then using lower frequency radio, we were able to get it down to like 2. Now, it doesn't mean that these are the only 2 models, because we still have many more models in parts of space to try to understand. But what it shows you is that by combining information, we can start to go further to kind of pave the way to understanding which model is actually correct. Another new horizon is going from making snapshots to making a movie. And this is a visualization just to show you that the black hole in Sagittarius star is smaller, and the time scales over which things change, it basically depends on the mass of the black hole. So a smaller black hole will orbit, all the astrophysical stuff will happen much faster. In Sagittarius A star, it happens on time scales of minutes to hours. And our telescope is not good enough to capture all that. So when we look at Sagittarius star, we're basically kind of averaging it all out. We're just adding everything up, and we miss out on this. M87, if you look very closely, this thing is moving. It's changing on timescales from weeks to months. So when we look once a year, we're only seeing, again, a snapshot. So there's a problem that our telescope isn't good enough to capture this, and we only get this once a year. Now, already from 2017 to 2018, the ring shifted 30 degrees. We don't know what it means. There's a lot of interesting things. There's a lot of theories about this, but this is the first frame in a movie. But if you do it once a year, you can imagine we'll get 30 frames in 30 years. That's not very efficient. So we need to sort of switch modes, and we have to talk to the people who run these telescopes and basically say, we need more time, more frequent. And so we're going to do a test of this in 2026. We're going to try to do a more condensed campaign and see what happens on M87. But if we want to do a movie of Sagittarius star, we need a better telescope. And this is where the new expanded array comes in. So if you look here, in yellow was the original array, and then basically you start to see some different things. Oh, and then green came a little bit later with the ones that were added more recently. And then in white are proposed sites for expanding the array, which will help us see more structure and also improve the amount of light that we could see. And here in Namibia is the AMT. This is being funded. Now, I think some of you might have seen all the talks. We've all come here and given talks, but Heino Falke and Rob Fender are my colleagues in this grant, which is funded by the European Union. So this is a sub-project, and each of these are being contributed. So these are US-based projects, European-based projects. We're somewhat European, but we're partnering with UNEM. Hiko and Lot are in the audience here. They're the first 2 PhD students in astronomy here in Namibia. And some of you might have seen the mobile planetarium. This project is also really doing amazing outreach. And so Sigrid is here, Delight's here. They're doing work to actually, all the students are running this project to go out to like rural schools and to turn on kids to astronomy. It's really great. But what we want is in 10 years or so, this project should be fully, operated and run by Namibians. And so we need to actually build up the group and create a pipeline of students from kids up to adults, and that's something else that's part of our project. So anyway, there's 2 potential sites. One would be the Gamsberg. This is a discussion at the moment with the Max Planck, who bought it in 1971 for astronomy, and the idea is that they're going to sell it back to UNAM for a fair price, apparently. This is a very interesting discussion. But we don't have a road up to this mountain, so this is the ideal site. And so what we're trying to do is think about another site, which would be where this HESS telescope, this gamma ray telescope is, that we used already together with the EHT. Here's a picture of Lot with one of my students who was visiting when we were here last year. It's a really fantastic telescope. If you haven't been, you should definitely look and go check it out. But one of the ideas might be that we start here and then move it up to the mountain once the road is built. But once we have it in place, here's Namibia, and you could see that you add these extra red baselines. And what it means is that this is sort of the model of what you think it might look like. Now, in the early times of the array, we get kind of garbage. We have to like integrate it until we can get everything together. If we add the AMT, we can actually start to get a good image already earlier, and that will allow us to get basically triple the amount of time to start to be able to make these dynamical movies. And then we can start to see structures maybe moving around. So the Africa Millimetre Telescope at the AMT is going to be very important, and it's the first expansion project from the EHT. It's also important to note that this will be our telescope. This will be yours and all of us together. This is something that means that we can use this more often. We don't have to wait once a year, and there's a lot of other science that's going to happen. Now in 2018, and I put this on the poster, here's the multi-wavelength, so we see the black hole and we see the jets. We also, you can't make a picture of it, but we saw a big flare in the gamma rays. So this is with Hess, and this is what basically AMT would be contributing to. And so the combination of having AMT on the Hess site is actually pretty interesting, because in real time you can look at these black holes changing. So I'm almost done. Some of you heard Rob Fender, my colleague, talk about the fact the sky is flickering. There's lots of little black holes and neutron stars and things flickering on and off. When we're not using it in this mode to study the big black holes, the idea is to use the AMT to study what are called transient events, so these kinds of objects that are flickering on and off. And it'll be one of the first times that anyone has ever done this in this particular wavelength, and it's the first facility that can look this way in the entire southern hemisphere. So I'm basically done, and I'll just summarize and say, it's been really a whirlwind century. We've gone from this idea of imagining black holes to actually making the first images of them within basically 100 years, and that's pretty amazing. And the EHT is really a benchmark for testing general relativity, and I would just say, oh my gosh, we can actually see black holes. So it's pretty cool. Black holes are important players in the universe. They're not passive. I hope that this talk maybe gave you a bit of a sense of the ecosystem that black holes contribute to. And there's just lots of cool things about black holes that I didn't have time to talk about, so I hope you have some questions. And the AMT here in Namibia is really going to be the first expansion of this network of telescopes. It's very exciting, and it's going to allow these first movies and a range of really new science. And I hope that over the coming decade, while we're all coming to visit more often, all of us in the team are becoming visiting professors here at UNAM, which is very exciting. We can show you continually how this project develops and what we learn. So thanks for your attention, and ask me even silly questions.
Thank you very much, Sera, for this
the lights back up,
this brilliant talk. Not both at once. I assume there might be some questions in the audience. People say there are no silly questions, so just try.
The silly questions are the hardest ones usually.
Brilliant, thank you so much. Just two quick questions. I've heard something about Hawking's radiation. Is that the same thing as that you described in terms of those jets?
No, it's a good question, because you hear about black holes in this radiation. Hawking radiation is like a quantum effect in a sense. It's basically like if you have a particle that escapes the black hole in a sort of, there's a probability, a very tiny probability that a particle can escape, because in quantum mechanics there's always this uncertainty. And so what that means is that over time a black hole can shrink by giving off this radiation, but the radiation is like a trickle. We're talking about something like 60 orders of magnitude, I think, less than the kinds of things that we're seeing. So it's completely undetectable. Even if you just looked at an isolated black hole, the amount of radiation would just be astronomically tiny, in the sense that we would not be able to detect it with today's telescopes, and probably not the telescopes of the next, even decades. It's a really, really small level, but it's an excellent question. It's just not the kind of thing. What we're seeing is light that's being created from more normal, not even quantum processes, but just kind of the same processes that fuel stars and nuclear processes and things like that.
And the second one is a silly question. Are wormholes real?
So this is, we don't know. They're mathematically possible, and there are models that have wormholes in them. But what they look like and how you detect them, so one idea is that maybe there's a white hole on the other side of a wormhole. Well, we've never seen anything that looks, or fits the bill for that. So I think the answer at the moment is the jury's out, right? There is a theoretical framework, not everyone agrees with it, that can predict wormholes as part of the, the space-time, but we haven't found one. There's no proof of this. We don't know which theory is correct.
Thank you. I just want to leverage off his two questions. At the beginning of the talk, I was actually scared of black holes and the gravitational pull, but now I'm scared of the jets. So if I happen to find a wormhole, where can I move? Because it seems like these jets are very powerful.
This is an excellent question. In fact, the jets from a black hole, when they're on, an active black hole, can provide a huge amount of cosmic radiation. So basically, I'm not sure if you're aware of, have you heard of solar storms? We've been going through them quite recently. The sun's in an active phase. And when that happens, the sun is giving off high energy particles, which are radiation, which is toxic for humans. Our atmosphere and the magnetic field of the Earth is protecting us from this. There's a lot of stuff in outer space that gives off similar things. The jets from black holes are very similar. But there's a point at which if you had a jet really full on pointing at the Earth, it might toast us a bit, right? And so in fact, we have you can find images of the jets. I'm trying to think, I think you would know this, Centaurus A, I think, jet encompasses star systems. These jets are enormous. As I said, they're basically billions of times longer than the black hole. They're bigger than galaxies. So when they turn on, there's lots of star systems that just happen to find themselves in the path. And we have to think that, most star systems have planets now. We're looking, there's going to be life out there, and there has to be, systems that are dealing with, interactions like this. We also know that if, for instance, a gamma ray burst or supernova, some of these cosmic explosions happen too close to Earth, that could be problematic. So I would say there are scary things in space that one should keep in mind. However, the most immediate danger for us, I would say now, is climate change. So that's a little more short term.
Okay. I have 1.5 questions, I guess. The first question would be, what is your favorite black hole or black hole simulation? What's your favorite of the simulations you have?
Okay, that's easy because Sagittarius A star, the one in the center of the galaxy, that was the first black hole I ever studied. I actually did a lot of work studying that black hole back when I was a student. So I'm quite fond of that black hole. And when I saw the first image of it, it was actually kind of emotional for me. So that's my favorite black hole, although I like them all. And then the simulations, of course, are the ones done by my group, of course. Is that the half question, or yeah? Okay.
Thank you so much. This presentation's been amazing.
Oh, thank you.
What's in a black hole?
Honestly, we don't know. That's a big problem in the sense that anything that goes in, we lose the information about it. So a black hole grows by what you put in it. So if you throw, people into the black hole, it will grow by the amount of mass of those people, but we'll never know which people it is because they can't get out, they'll never be able to get out or communicate with us. So there's a lot of debate about what information is lost. This gets into theoretical physics. People have ideas that maybe some of the information gets encoded on the surface of the black hole in some way. But this is very much still in the theoretical realm, and we have currently no way of knowing. So it's a mystery.
Hi, I've actually got 5 questions, but I'll do one at a time. Would this new work get us any closer to understanding why there are no medium-sized black holes?
So that's a good question. So maybe just for the rest of the audience, I mentioned that there are black holes that form when stars explode, and those are what we call stellar mass black holes. And then there's supermassive black holes, which are these ones we find in the center of galaxies. Those black holes didn't start out supermassive. They had to grow over very long time scales. And so there should be something in the middle. whether it was the original seeds of the black holes that maybe some of them didn't grow. So there should be this population, what's called intermediate mass black holes. So far, we have never found one. My answer to that would be that I don't think this project is going to be the one to do it. And the reason is that those types of intermediate mass black holes are probably not very bright. And so we need something more sensitive than this particular technique. So people are looking for them, and they are using like radio and X-ray, these wavelengths that I mentioned, but they're using much more sensitive facilities. And we have, our specialty is having this really high resolution of being able to see like really small things, but they have to be relatively bright for us to see them still.
Hi, no, it's absolutely everything you say is completely fascinating. Can you say something about how the study of dark energy and dark matter might have a radical effect on how you perceive things, because they're talking about Einstein even being like Einstein not replaced, but superseded Newton, that they might have to start recalculating stuff based on that.
I mean, I have to say with a caveat, so dark energy and dark matter are not my fields, right? And they don't necessarily impact on what we're doing. There are theories that black holes may be a good ground for, the same things that lead to the creation of black holes in the first place in the centers of galaxies involve probably dark matter, and that dark matter, carries most of the mass in the universe and thus, is condensing there. But the discovery of dark matter is still something that's very much up for debate. I think everyone in the field still more or less believes that it must exist because the measurements are kind of hard to get around. Besides some of the more indirect measurements, there's the fact that we've seen colliding, these clusters of galaxies that I mentioned, they collide, and you sort of see the gravitational pull of stuff pass through. So the stuff that's very heavy, it's invisible, but you detect it via these gravitational lensing, and then you see this bright stuff stuck together in the middle. So we know that there's different types of matter. But I think there's the field at the moment, especially around dark energy, is also going through a bit of a sense of, I wouldn't say doubt, but like flux. There are some experiments that don't agree with each other. Nobody has found, for instance, no one's found the particle for dark matter, and dark energy, different experiments are somewhat, disagreeing with each other. There are alternate theories. I think that these are probably on solid ground, but, we don't have like the definitive model worked out, so these are very active regions. The work that we're doing probably doesn't intersect exactly with this because they're very different detection techniques, but they are interrelated topics. But I don't have a good answer for you about what the answer is right now because honestly, it's something that's very much discussed. I think one thing that maybe is interesting for you is the fact that the new telescope, sort of the follow-up to Hubble, which is called the James Webb Telescope, JWST, is finding, for instance, very large black holes early in the universe that is kind of changing some of our models. And also there's some questions from other experiments about, the growth of, some of the things that are used to measure like dark energy. And I suspect that within like 5-10 years, we're going to have a much clearer answer from these new facilities that are coming online. Yeah.
Thanks for the talk. First question, I would love to hear your Shaggy Dog story. Second question, can you explain in 5 seconds primordial black holes?
Yeah, okay, so I'll answer the second question first. So there's ideas that early when the universe formed during the Big Bang, there could be like little fluctuations, and some of these could form. There's different processes that can lead to them, but basically you end up forming little tiny, like microscopic black holes, but some of them can go up to many orders of, like tens of solar masses, and also even heavier than the black holes that we're already detecting. So there are constraints on what kind of black holes could be primordial. And right now, that's coming more into the field of gravitational wave detection. So I haven't really talked about this, but there are ripples in this fabric of space-time that are now being detected called gravitational waves. And the sources of these are mostly two black holes that are merging. And some of them seem to be anomalously, the weight of them is either larger than we might think would form from stellar processes or too small. There's sort of a mass gap. And so people have said, maybe we're detecting primordial black holes for the first time. These would be black holes that form in different ways than the death of a star, and you might be able to tell the difference between them because of their mass or, you know, the system that they're in. Okay, so the shaggy dog story, oh, whoops, sorry, let me see if I was gonna try to find, I had a slide on it. Yes, okay. So it's actually kind of, yeah, maybe, can you see or do I need, okay, here we go. So this is, when people came from this gravitationally collapsed star idea, a lot of people thought that John Wheeler, who's a very famous, he's the guy, many of you have maybe heard the term, black holes have no hair. He was like a marketer, everyone knows that term. And what he was saying is that black holes are very uncomplicated. They can basically be described by their mass, by their rotation or their spin, and this thing like their charge. So they don't have a lot of like personal characteristics. So a lot of people said, and most people I think even in our field think that he was responsible for coining the term black hole, but it was actually this guy, Robert Dicke, who was a British physicist, and it came from actually a colonial story. So in India, in the period of time where the British had the Raj, you know, and basically were occupying India, there was a garrison there, so it wasn't fully under control, and they had a garrison of soldiers there, and the soldiers had a prison there that they would put like local, local Indians who were like uprising against the British. They didn't like that, so they'd throw them into this prison. And the joke kind of among people was that if you go into this prison, you never come out. So they called it the Black Hole of Calcutta. And what happened was, of course, the locals weren't too happy about this. At some point, they overthrew the garrison, and they took 200 or so of the British soldiers, and they shoved them into this tiny prison, and most of them died. And it was a very traumatic thing. So this is actually like a drawing that was in the newspapers. It went into the papers at the time. If you go to Calcutta, apparently one of my students who's Indian told me that there's a plaque somewhere that you can see. But so this happened in the 1700s, but it's made its way into the British lexicon, apparently, that people started to talk about black holes as where you couldn't find things. And Dick grew up hearing his dad, I think, was his father or somebody saying they had a joke that if you couldn't find the socks, you know, the black hole ate it, or whatever. And so when they were needing a new name, John Wheeler was saying, we need a new name for this, it's too long. Robert Dicke during the talk said, what about black hole? And everyone was like, wow, that's perfect, you know, because light goes in, it doesn't come out. It just sort of stuck. And it also had a little bit of a sinister, I think, feel to it. So there's a combination. It actually has a bit of an interesting history that many people don't know. So I thought, that's the shaggy dog story.
Actually, I want to know if there's a lapse between climate change and black hole.
Sorry, can you repeat the question?
Is there climate change and those black holes are lapsing to one another?
I'm sorry, okay. No, I mean, I would say definitely not, because, you know, again, remember I was talking about the fact that black holes are very, you know, distant from our point of view, and they're not directly affecting, you know, us on Earth. I think when you think about something like climate change, you have to look at what's really encompassed within the atmosphere of the Earth. Now, it's not a stupid question to say that things in outer space can affect our climate. We do know that there have been effects of cosmic events that can impact, for instance, solar storms and other kinds of things. There's records of this, that our climate has had evolution due to cosmic events. So, I mean, I guess in principle, you could say that perhaps like some exploding nearby object that became a black hole might have impacted our atmosphere at some time in the past. But currently, I would say that's not what's going on with us. Does that answer your question?
Yeah, thank you.
Okay.
Yeah, thank you very much. I think with that we had quite a couple of very interesting and intriguing questions, and I think it's time to thank Sera again for
Thank
this
you so
brilliant
much.
presentation. While having done so, I want to invite you to a few things. Firstly, there is a presentation next Thursday that we have here in the very same premises about the, no, it's not hunting, poaching of pangolins. And well, it's quite a different topic, but I can imagine that quite some people in the audience might be interested in both topics. And then I open the door for this, because at the back side, while you walk out, you will notice that we'll have the Southern Star Party happening in early September, and you're obviously very welcome to join us at Grossbarmen for a weekend of stargazing. With that, I want to invite you to stay with us around for a little for socializing. There is some reserves there at the back for drinks. While doing that, but just before doing that, please help us to get the chairs a little out of the way. And if you don't mind, also please don't forget to leave some donations with us so that next time we still have some reserves and drinks for the next group of people here. With that, I thank you all and wish you a very good evening.